back, everyone, to our discussion of related rates with this example where we inflate a balloon. We're inflating the balloon at a constant rate of 10 cubic inches per second. We could ask, how fast is the diameter increasing at the point when the diameter is 10 inches? Now, if you haven't watched the previous video where we started this example, you need to go back and do that. Because here, our purpose is just to tie up a few loose ends. In particular, we want to talk about if we had set up the problem a little differently, if we'd identified slightly different variables or in a different order, how that might affect the work involved. Hopefully not the answer if we do everything correct. So let's take a look at the details. So once again, our setup is we have a spherical balloon, a nozzle in the side where air is being forced in at a constant rate, dV by dt equal to 10 cubic inches per second. Let's set up our variables. In this problem, time, I'll keep that as the independent variable. That is a pretty good rule of thumb. This time, however, I want to reverse diameter and volume. So I'm going to have volume depending directly on time. See what happens. Actually, instead of just listing diameter depending on volume directly, let me stick in an extra variable here. I'm going to kill two birds with one stone, I hope, by showing you what happens when you have more than just three variables present. The chain rule for this situation says dd by dt, that's actually the quantity we're looking for, is equal to dd by dr times dr by dv, dv by dt. Now, this is easy. You're given that rate of change. This one is also easy. From the formula, the diameter is twice the radius. You can take the derivative and get 2. So there's a constant 2. There's a constant 10. And this is the one that takes just a little work, but you can compute that algebraically. If you start with volume is 4/3 pi r cubed and solve for the radius, well, that's one way to do it. Solve for the radius here. And then take a cube root to solve for r. This is why we didn't want to go this way. I wouldn't advise. If you're having to take cube roots, then maybe you should think about, instead of writing r in terms of v using a cube root, it might be nicer to have v in terms of r, as it was originally given in this formula, and that would simplify the formula and the derivative. So that would be your tip, that maybe these are in the reverse order. But I just want to go ahead with this approach and show you what happens and show you at least that you get the right answer this way. Now, if I take the derivative algebraically, I'll use the power rule. And since I have a 1/3 out front, maybe I'll just use the chain rule as, you know, the derivative of a 1/3 power is 1/3 that quantity to the minus 2/3. The inside stays the same, so that's 3v over 4 pi, and then the chain rule says you have to multiply by the derivative of the inside. There we are. The 3's will cancel, and having done that, we have something just a teeny bit simpler. Always simplify whenever you can. Now I'm going to substitute all this information in to my chain rule. Derivative is twice the radius. So the derivative there is 2. This derivative, I just worked that out. Times 10. Constants simplify somewhat, so 5 over pi times 3v over 4 pi to the minus 2/3. Now we have to evaluate this at the value d equals 10 inches. When the diameter is 10 inches, you can see from this formula that the radius would also be 5 inches, and then you can substitute that into the formula for volume. 4/3 times pi times 5 cubed is 125, and when you multiply that out, you get the volume of 500 pi over 3, and that's cubic inches. Given those values, you can substitute that into this expression, and we get that the required rate of change of diameter with respect to time, it's a variable, but you evaluate it at d equals 10 and get a constant answer, a numerical answer. Now here's where it gets a little ugly. This minus 2/3 power, 3 over 4 pi times, we just worked out what v is. Substitute that in to the minus 2/3. Immediately stuff starts to cancel and simplify. This goes into here 125 times. Cube root of 125 is 5, and then 5 squared in the denominator. So this whole thing comes out to be 1 over 5 pi. And that's inches per second. The fact that this all canceled out like this was your tip that maybe we should have been doing it the other way around in the first place. We were doing a lot of extra work for nothing. Anyway, the point is to see that if we're careful, we do get the same answer. This is exactly what we had before, numerically. 0.064 approximately to 2 significant digits. And the thing I really want to say here is you get the same answer. It's not a logical dependence of variables or causal relationship, a sequence of each thing causing the next that is important. What is important is to try to write the variables in such an order that you can easily take the derivative by the formulas that you have available here. We gave ourselves more work to do by having to write r in terms of v as a 1/3 power. If you had it the other way around, then you would be dealing with a derivative of a cube. That would be much nicer. But we have the same answer, so lesson learned.